So I'd like to kick off after the break. We're going to hear from Warwick Holmes. Warwick's with the European Space Agency, and Warwick has been to Murchison before, and we're really pleased to have him back. And he's going to be giving us an exciting talk about the Rosetta mission. Over to you, Warwick.
Right, thank you, Graham. Well, it's a great honour to be here again to speak to you again about the significance of the Murchison meteorite, which had an enormous impact on a mission that was defined by the European Space Agency. And that was to try to build a spacecraft, fly 10 years through the solar system to land on a comet. And so today I'm going to explain to you the significance of that mission and how there's this inextricable link between the Murchison meteorite and the very fact that they even built this spacecraft. And that is that the incredibly exotic carbon chemistry that was identified on Murchison triggered an enormous interesting, or what process, what chemistry is on comets that could possibly explain this, or asteroids. And so European Space Agency 25 years ago started defining a mission to build a spacecraft that would fly for 10 years, 8 billion kilometres, 4 times around the sun, building up velocity to match the speed of a comet. Comet 67P, it's called, Churyumov-Gerasimenko, named by 2 Ukrainian astronomers. And then to land on the comet with some very sophisticated instruments, a mass spectrometer. Trevor, you'll be amazed to see that instead of taking up the size of a room, we built mass spectrometers the size of a shoebox. 2 of them, in fact. So all of this, and I really have to emphasise this, was driven by the discoveries found on the Murchison meteorite. So, just very quickly, my role in this mission was, I worked for the European Space Agency for 30 years. Avionics Systems Engineer. I've built 10 different spacecraft, involved in the design, integration, testing of 37 tons now of satellites which are in orbit. And that involved working on an infrared space telescope, X-ray multi-mirror emission telescope, a 20-ton segment of the space station, first 4 Galileo satellites, which are what the European version of GPS is, Meteosat weather satellite, Probe 1, which does remote sensing imaging, and most important of all is Rosetta. So I've had a huge experience building satellites with the European Space Agency, but by far the most important is this one, Rosetta, driven by the chemistry of Murchison. I'm currently working with the European Union on the next generation of Galileo satellites. Okay, so we've already heard from several scientists today what the significance is of the formation process of our solar system, and that chemistry of exploded stars forming an accretion disk that then help to form our solar system, the planets and the sun. And what role does Murchison have in this, and or comets? And so this is the purpose of the mission, is to try to link some of these processes together to understand what actually got the formation of the Earth and human life on planet Earth. So the fundamental question that scientists want to answer is, how do we get from this supernova remnant, an exploded star, where elements are made, this process of nucleosynthesis, creating the chemistry that helped form planet Earth, and which is obviously a very complex process to get from that vastly huge expanse of exploded gas into planet Earth with water and surface to this intelligent life. Yes, we won't go any further, will we? In fact, this man right now is affecting my job in Europe because I have a British passport as well as Australian, and because of Brexit, I now can no longer work on a European Union program. So thank you, Boris Johnson. But everyone's ignoring that, and they're just still giving me work anyway. So, okay, so this is a computer graphic of what we believe the early formation of the solar system looked like. We have this accretion disk where material is condensing and collapsing and coalescing together to form planets. And this is the time when cometary bodies were first being formed on the outer extent of the solar system. Now, of course, in this image here, the sun is already burning. Otherwise, there wouldn't be any light to even have an image. Okay, so the formation of comets is even before this graphic. And that is, it's cold, and it's dark, and a very, very different environment that we're familiar with today. But this is the environment in which comets formed, and this strange chemistry, this carbon chemistry that we're seeing now inside Murchison. There's more than 100 different amino acids and precursors of amino acids, sugars and esters and all sorts of weird carbon chemistry. This is all forming in this outermost extent of the solar system, and the question is why? Well, what's going on there to create such complex carbon chemistry, and maybe the precursors of life itself? So this, of course, is an image of Murchison, which we all know. We won't discuss that anymore. We've had a lot of discussion about that. But this is a video showing how they found deep inside Murchison these amino acids, of which I believe now there's been more than 100 have been identified. And this is adenine and guanine. And these are 2 of 4 amino acids that form nucleotides in RNA and DNA of the human body. So the very chemistry that's in every single one of us in this room today has been found in the Murchison meteorite. And this is what they believe, or hope to believe, and prove, is this mechanism helped to seed life on Earth. So that if water came from cometary bombardment, also this carbon chemistry came there, and to create this organic soup out of which the very first life forms formed. So the very first single-cell amoeba, stromatolites, which we know from Western Australia, and then life evolved and the Darwinian principles, and created life as we know it today. But that very, very original chemistry, there could be even atoms of these molecules in our bodies today, which actually came from meteoritic or cometary bombardment of the Earth about 1.3 billion years after it first formed, what they call the secondary bombardment. Now, the reason I say that Murchison has driven the definition of the Rosetta mission, Murchison has driven the Rosetta mission, is because we've matched 3 potential comets which have trajectories which we believe to be close, and this is where Curtin University come in to help us try to substantiate this, that we believe there are 3 comets which have matched the orbital parameters of what could have been the Murchison fragment of the Murchison meteorite that came in. Comet 15P Philae, 107 Wilson-Harrington, and this Canadian fireball event, they call it Radiant 198. And they have this thing called the D-discriminant method, which is they look at the 6 different orbital parameters of these heavenly bodies, and they say they're within 1% of what Murchison was to have hit the Earth when it did it, 28th September 1969. So immediately, we're interested, well, let's go back to a comet and see if we can really find in situ, in the source itself, the same chemistry. Now, to do that is extremely complex because comets are very far away from the Earth. Some of them have had their orbits modified by Jupiter. They call them Jupiter family comets, which Jupiter's helped by its huge gravity to reduce the orbit for us, which means it's easier for us to catch. There were 22 candidate comets which we could have gone for, of which we chose the 4 best, which could be caught by the full energy of an Ariane 5 launch vehicle, which I'll show you soon, together with gravity assist. Now, gravity assist is where we use the orbit of planets around the sun to help accelerate our spacecraft. And it's like a free lunch you get in terms of energy. But I'll show that to you coming up. So we had these 3 cometary bodies which we believed could have been linked to Murchison. So we defined the mission, and this is what the spacecraft looked like. It looks like a fairly general purpose satellite in the sense that this is the body of the satellite here. It's about 2 meters by 2 meters by 3 meters deep. So 12 cubic meters is the volume. On here is little Philae, which is the lander, which is now on the surface of the comet, together with the main mother spacecraft Rosetta, which we put on the surface as well at the end of the mission. That was after 2 years of tracking the comet. And this mission flew for 10 years after launch to catch the comet, 4 times around the sun, getting these gravitational assists, and travelling a total distance of 8 billion kilometres. 8 billion kilometres to catch the comet, to put the lander down, and then follow the comet for 2 years in orbit around the comet as we went around the sun. An incredibly, incredibly complex and ambitious mission. NASA actually say, and I was just checking this with Mike today, that it's the second most complex interplanetary mission that's ever been attempted, after the complexity of, for example, landing on the moon. So this is a close-up of the Philae lander, and this is about 1 cubic metre in volume. It carried 10 scientific instruments, including a mass spectrometer, not the size of a room, Trevor, that size of a shoebox, a gas chromatographer, RF tomography. It had microphones on each of the feet, 3 microphones and 3 speakers. And because we were in contact with the comet, unlike the vacuum of space, we could actually do seismic sounding. We would like the ping from a submarine. We could ping acoustic signals into the structure of the comet, and the rebound of the sound gave us what the internal physical structure of the comet was, together with RF tomography, which is these antennas on the left and right, which did like a CAT scan through the comet. So we had a transmission source on the lander, and as Rosetta went around the comet, we were doing a CAT scan through the comet. Using the same principle as that machine, you see patients going into in a hospital. So we had these very sophisticated scientific techniques for interrogating the comet in situ. This was 500 million kilometres away from Earth, 2,000 times further than the Moon. The Moon is actually a long way away from the Earth, which a lot of people don't realise, 400,000 kilometres. But this really was an enormous distance. It took 28 minutes at the speed of light for signals from Philae and from Rosetta to get to Earth. 28 minutes at the speed of light, just waiting. So when we touched down, we had to wait 28 minutes to know that we had actually touched down, because that signal was travelling from the comet at the speed of light. And that's how long it took. So these are these immense distances which are involved. Now this is just a photo in the year 2000 when I was involved in making the very first flight model. We built two models, a flight model and an engineering model. The engineering model is here on the ground today in the control centre in Darmstadt, Germany. And we use it for testing and solving problems while the other satellites are flying off towards the comet. I put this in black and white to make it look older. Okay, so. But this is in Turin, in Alenia Spazio in Italy, and this is actually, they had the contract for building the spacecraft, and it took 4.5 years to build it. This is a photo towards the end of that process. This is up in Holland, where I was performing the environmental test on the satellite. So this is a completed model, which then went down to French Guiana, where we then did the launch. This is where the European Space Agency launches all their spacecraft. And there's a dedicated Ariane 5 just to launch Rosetta on this unusual trajectory to get to the comet. So there are 11 instruments in total on Rosetta. And this front surface here is where we have all the cameras and the spectrometers. And there's an atomic force microscope, which is another very complex instrument for analysing dust grains. So what we did is we took the laboratory to the comet, not the comet to the laboratory. So you might hear in the next few months about Hayabusa 2, which is a Japanese mission that's actually just touched an asteroid and picked up some material from the asteroid, which will then be returned to the Earth. In fact, it's landing in outback Australia. They'll be bringing a few grams of asteroid material back to Earth, which will then be analysed like crazy in the labs here on Earth. Only a few grams, not the 100 kilograms that we have of Murchison. But the amount of energy it took us to actually get out to the comet, we couldn't reverse that. There's not enough fuel that we could take. We couldn't do reverse gravitational assist manoeuvres because they're extremely difficult. So we had to take the laboratory to the comet. And this is why all this complex engineering and the avionics to build all these very sophisticated scientific instruments to actually make measurements on the comet itself. So now this is Philae. This is on the vibration table. This is where I rather regret this image a little bit because, as always, there's a huge amount of stress doing this kind of work, and time is always running out and going wrong. And I had to connect these accelerometers here onto the feet of the lander to measure the vibration that Philae would experience during the launch of the Ariane 5. There's enormous vibration and shock levels when the rocket's going off. And I was actually putting these things on the feet of the lander. And I wish I'd just for 30 seconds had stopped and thought, hello, little foot. One day you'll be touching the surface of a comet, which it is today. I just wish I'd taken a few moments to think, that foot pad there, both of them are now touching the surface of a comet 800 million kilometres away from Earth. So that's the vibration table. We shake that very hard at the same level as the shaking level of the rocket during the launch. So this is, this is just a graphic showing a list of the instruments, of which there's very many. So in fact, I mentioned there's 21. There's actually more than 21 instruments because when we transmit the signals back to Earth, the transmission signal itself becomes a scientific experiment. In terms of measuring the Doppler shift, it tells us the mass of the comet. Also, we're transmitting sometimes through the coma, the gas and dust cloud around the comet, and that actually gives us scientific information. Just transmitting the instruments, the information of the other instruments back, we can get science on top of. It's like a vicarious scientific instrument. So there's an enormous amount of science that you can extract in situ in a close orbit to the comet. Here again, this is some of the list of instruments on Philae, the lander. This was specifically designed for landing on the surface. Now, as it turned out, when we touched down, there are 4 mechanisms which are trying to hold onto the comet because the comet's extremely small. It's 4 by 3 by 2 kilometres in size, which is ridiculously small in terms of mass and size. It means it's got no gravity. It's got 100,000th of a g, which is effectively 0. So when we touch down, how do we stick onto the surface? Well, this is where these 2 harpoons come in. There's these 2 harpoons which fire into the surface. They go 5 metres under the ground. There's a pyrotechnic charge which fires them in. and a little umbrella opens up, and we pull back with a Kevlar wire to pull us down and hold us onto the surface. There's a little thruster at the top here, which is used for firing a cold nitrogen gas for about 10 seconds to push us down while all these mechanisms are drilling in. There are drills here, which actually try to grab the ice as well by drilling into the ice. The two harpoons here and the thruster did not work. The reason is that 10 years in space at 75 kilograd of radiation at minus 200 degrees Celsius in the pure vacuum of space had changed the chemistry of the pyrotechnic charge, which had never been in space for 10 years before. We didn't know that that was going to happen. The little cold gas thruster at the top had a little wax plug. And we had two 40-watt heaters to actually melt the wax. The wax had changed its chemistry. It was no longer wax. It was turned to concrete or something. But we turned on the two heaters and they didn't melt, so we actually couldn't fire the thruster. So the weird chemistry of deep space and high radiation levels, which has never been done before, actually caused these mechanisms to fail. So the poor old lander bounced, and I'm going to show that to you on the model here. But despite these things going wrong, still 90% of the science that we wanted to do on the surface was achieved. We just didn't know where it was done, and in the very last 3 weeks of the mission, we found Philae on the surface, which then helped us to match all the scientific measurements from the orbiter to what was on the surface to get the whole picture. So it's all good news in the end. Okay, so having defined what we wanted to do and how to do it with the spacecraft and miniaturizing the instruments, how do we get there? Now, the problem we had is that there was an enormous distance to travel, 8 billion kilometres, and so this shows this gravitational planetary assist that we did. So it took 12 years, 10 years to get there, 2 years following the comet. Okay, so this is Earth here, and we launched on 2nd of March 2004. The white line is Rosetta. It leaves the Earth, and we go forward to the Earth, and then we catch up again. The Earth catches up and gives us our first gravity assist, 15,000 kilometres an hour of speed, just using the gravity of the Earth. It makes us go a bit further out. We come back in again for our second gravity assist, but we're in the wrong position, so we use Mars to bend us back in again to get our second gravity assist from Earth, which is happening here. That's at 13th of November. Second, another 15,000. So we've now got 30,000 kilometres an hour of free energy. This is a bigger orbit going out through the asteroid belt now. So we actually flew past an asteroid called Steins. Just took some photos. It was a good test for the comet, though. We tested all our instruments and there's our third gravity assist. 45,000 kilometres now of extra speed, not using any fuel. Okay. So another asteroid we flew by, Lutetia. And then this is a comet out here, Comet 67P. This is the orbit of Jupiter, so we're going out past the orbit of Jupiter. And we had to go into hibernation. It was so far from the sun, it was a solar-powered spacecraft, we had to turn everything off. Just one little timer on board, woke us up 2.5 years later for a 20-hour engine burn to try to match the speed of the comet. We then we did the rendezvous, we did the arrival on 13th of August, and then we were looking immediately for a landing spot. For about 3 months we started looking for a landing spot. 14th of November was when we put Philae down just as the comet was becoming active. So we did what we call the cold chemistry on the comet. So then the Rosetta is following then the comet, and we came to the perihelion here, which is the closest point to the sun, and this is in 6th of August 2015. And we had planned to finish the mission just after the hottest part. It turned out that the spacecraft was in such good order, we went out right out here again to September, and we got an extra 6 months of science that we weren't expecting. So a very complex trajectory, but after all that calculation, there was millions of hours of simulated computer time to calculate those trajectories, reverse engineering of where we wanted to be at a certain time, the positions of the planets, the time of the launch. We had to launch the Rosetta mission with a 6-second launch window. If we missed that 6-second launch window at French Guiana, 2 billion Australian dollars of funding would have been lost. There would be no science, because you cannot catch the comet with all that sequential series of events that had to be timed within seconds to actually do the mission. Okay? So that's some of the criticality of that mission. So we built the spacecraft, and this is it in a thermal vacuum chamber. So this is the 12 cubic metre spacecraft, a 2,000 cubic metre vacuum chamber. So this is the facilities they have in the European Space Agency. And we can see the temperature ranges minus 107 degrees Celsius to plus 150. That was the operational temperature that Rosetta had to go through from the launch when we were at Earth, close to Earth, to out past Jupiter. You can measure about 300 degrees Celsius variation. So imagine if you've got your TV would work in the fridge. So say you put it in the freezer, 0 degrees, and your TV's working. Put it in the oven, set it to 300, and tell me if it works. Okay, the whole spacecraft had to operate within these margins for 12 years, in fact. But I'm not even mentioning the radiation, okay? So, and the vacuum. There's the vacuum of space as well. So all these physical and environmental factors make it extremely difficult to make Earth-based electronics survive in this kind of environments. But we had to for the mission to work. Now, where's Alan? Can't see you now. Yeah, this is a very special video, Alan. Okay, very special photo here. This is Philae strapped onto the side of Rosetta, Rosetta being the mothership that carried Philae to the surface of the comet to do the deployment, the landing. And then Rosetta came down 2 years later. As Australians, can you see anything very special in this photograph? $50. I put a $50 note on the landing, it's mainly just for size. But then I realised, well, hang on, yeah, there's quite some Australian significance there. Okay, so how many $50 do you think you'd need to buy a Philae? We'll start at 2 million, okay? Because it's, what is it? No, it's 200 million Australian dollars is the cost of just Philae, okay? Out of a $2 billion program, so it's about 1/10 of the total cost of the mission, is just in that one little lander, okay? So now this is just some food showing what's inside the Philae, for example, and this is one of the most complex, compact little boxes of electronics I've ever seen that's gone into space. Just a seething mass of electronics. This is the harness wiring and the computers. And we've got these little gas bottles here, which is the helium used for the mass spectrometer, for transferring the gas and the dust through the mass spectrometer, time of flight spectrometry, mass spectrometry. This is a little 10 Newton thruster that didn't work. So in there's a wax plug which didn't melt. Otherwise we would have got 10 Newtons of thrust for 10 seconds, holding us down on the surface while the harpoons went in and the screws locked in. But that didn't work. But the important thing was we're coming down at 1 metre per second, 3.6 kilometres an hour. The escape velocity of the comet is 0.8 of a metre per second. So if we bounced off the surface, a hard surface, Philae would have hit the surface and bounced off and never come back. Because its escape velocity of this very small comet was less than our approach speed. So if we had a perfectly elastic collision, all that 8 billion kilometres and $2 billion, it would have bounced off. Imagine how embarrassing that was. Luckily, we lost half a metre per second of kinetic energy when we did the impact, so we bounced off at 0.3 metres per second, but we didn't know where we were going. And so we then had to, it took 1.3 hours to come back down again. And we had actually planned within about 150 metres we got within the point that we wanted to, from 22 kilometres up. But when it bounced, we then had to find Philae, which was quite a job. Okay, so I was very lucky. I'd worked for 4.5 years in the program building the spacecraft, so I was actually chosen to give the go for the launch from French Guiana. So there are 8 people involved in the launch. They're all around the world at ground stations, control centres in Germany, and ground stations picking up the signals from different, New Norcia in Western Australia. There's a big dish down there. I hope you can hear the audio here, but this is where we had to give the go for the launch. And so this is where I'm calling on the microphone to Germany, saying we are go for launch. We're separating out our umbilicals, and he confirms the message. And this is the point of no return. 6 minutes later, we had to launch within 6 seconds.
Copy that. So you went to internal power 070358, and I can confirm telemetry coming in.
Okay, so he's confirming we've gone to internal power, which means the umbilicals have disconnected from the rocket. We have to go. There's no way you can run back up to the rocket and stick them back in again, okay? It's point of absolute no return. We got the 6 second window, and off we went. So this is the launch.
De DDO. Attention pour le décompte final.
1,300 tons of thrust.
7,
It's about to happen.
10, 5,
So these are the umbilicals disconnecting, I was telling you.
2, 1.
Arms retracting, fueling arms. Takes 6 seconds to ignite the cryogenic engine. And then the solids go. The solids are about to fire. Boom, there they go. Off we go.
Allumage GAP, décollage.
We're standing 4 kilometres away, and the shockwave almost knocks you over. The energy coming out of that rocket is unbelievable. 70-metre long rocket, the flame is about 200 metres long. Okay, that's the sort of energy you need to get a Rosetta mission started. Okay, so really dramatic stuff. Yeah, that's the pinnacle of these space missions, is seeing the launch. So we fly for 10 years. We turn on the camera after hibernation, and this is our first images. oh my God, what is going on here? We were expecting a spherical potato-shaped thing, right? We incidentally never knew what Comet 67P looked like, because all we could see was the tail of a comet, the big gaseous tail, which is millions of kilometres long, reflecting the light from the sun. The head of the comet, which is 4 by 3 by 2 kilometres, from 800 million kilometres, you can't see. There's no camera, there's no telescope in the world that can resolve that small body from that distance. All we knew was that there was something at the head of this tail of the comet. So an entire mission was defined without knowing anything about what we were landing on. We had to design landing gear of a surface we didn't even know whether it was hard ice or fluffy powder snow. We knew it was very cold, and we knew it was frozen gases, but we didn't know what the consistency was. We didn't know the shape. And this turns out to be what they call a bilobate body, which is actually 2 comets stuck together. We've done a lot of chemical analysis now of the head and the tail, of the body of the comet, and they are actually different bodies, which have gently come together under gravity and just stuck together. The probability of that, way out past the orbit of Neptune or Pluto, is unbelievably, infinitesimally small. But almost every cometary body we've seen now, and even asteroids, appear to be bilobate. There seem to be 2 things stuck together. So there's some really weird physics and chemistry going on in the outer extent of our solar system. And here's proof. So, so we looked at this image and we thought, wow, it looks like a rubber duck. Because the head, the body, yes, it indeed looks like a rubber duck. Okay? So we'd flown 8 billion kilometres to find an astronomical rubber duck. So then we started taking some very, very complex images, and this is where we took our first colour image. We've got cameras with 17 or 27 different filters for all types of different spectroscopy, and this is a true colour image in a sense, in that the light being reflected off the comet has an albedo of only 4%. So 96% of the light that hits the comet is absorbed because it's extremely dark. This is not really real. This looks like a light brown colour here, but in reality it's blacker than coal dust. And incredibly small amounts of sunlight are reflected. This was out past or close to the orbit of Jupiter when we first had 5 astronomical units, so that's 1/25th the amount of light, or solar incident energy, is hitting the comet, and only 4% coming back. So we're getting incredibly small amounts of light to actually get these images. So we had very powerful cameras, and to then get colour images, you're even reducing the energy even more to look at just one specific colour. So the complexity of this image, taken this one 500 million kilometres away, to even see these colours in this resolution is a true triumph of engineering and science. So that's what the true colour of Comet 67P looks like, and you can see this brown tinge is evidence of the carbon chemistry. The sooty bitumen type colour, I guess you could call it, is in evidence just because otherwise it's not a white, pristine, snowy comet. It's got this colour to it. So we took tens of thousands of images and stitched them all together, and we've got this is the plane in which the comet is rotating around its axis of maximum inertia, and we can see this outgassing coming from the neck region. This is where the tail of the comet is formed, where the softest material is, and it rotates in this direction, and we can see this super high resolution. We can zoom in down to individual centimetres on each of these images to get incredibly high resolution imagery of the body. And this is what the computing power gives you today. If you can stitch together all these images, you make a digital elevation model, and you can see the landing was in this surface here, on the head of the comet. And so this is the kind of science that can be done with extremely powerful image processing. And behind that, on top of that, we can layer the spectroscopy, what the material is, and the atoms and the elements, and there's really an enormous amount of data which we can stitch together. So what did we find? We found these unusual features. This is not a crater. This is effectively like it's a well hole. It's a cylindrical hole that goes straight down deep into the surface, several hundred metres. And this is a vent hole where outgassing from the volatile components sublimating inside the comet blast out through the surface of the comet to form the gaseous jets and the tail of the comet that we see. And we can also then see this internal structure. One of the benefits we get is we can see deep inside the structure of the comet without having to drill a hole. The hole's already there for us. So, and they call it these goosebumps. They seem like, can't quite see it so clearly here, but this looks like there's lots of little goosebumps on the inside, or golf ball-sized nodules, which seems to be evidence as to how the the physical formation of the comet occurred. And so here's an actual vent going off. So this is 18-minute time exposures of Rosetta in orbit around the comet, taking a photo every 18 minutes. And at 13:24, boom, off goes a vent. And this is as we approach the sun, the incident energy from the sun slowly heats up the inside of the comet, vaporizes some gases. Now, sorry, something I forgot to tell you. 99% of the surface you're seeing here, not 90, but 80%, is frozen gas. So it's frozen carbon monoxide, nitrous oxides, carbon dioxide, methanes, here, hydrogen sulfide, for example. These are some of the gases, frozen. And so we're seeing solid gas is what most of the comet is made out of, apart from the amino acids, which are so complex they're obviously, they then become non-volatile. So really strange things happening with the comet. Now, this is where the story with Murchison comes in. So obviously an entire comet didn't hit Murchison 50 years ago, otherwise there wouldn't be anybody here. So the people put their hands up when they were here, they wouldn't be here, okay? Because they would have been wiped out by a 4 by 3 by 2 kilometre comet. But what happens is the comet does shed material. This is about a 4 metre large clump that broke off. Comet Schumacher-Levy broke it into 27 or 22 different pieces when it got close to Jupiter. Comets are very fragile, not very strong astronomical bodies, and they break up easily. So Murchison is potentially a 4 metre segment, or moonlet, that broke off from one of those 3 comets I mentioned in my second or third slide, that could have then come in close to the orbit of the Earth. The comet carried on past, but this little fragment came in, and this is possibly an explanation for the cometary origin of Murchison. So these mechanisms, that we found dozens and dozens of these things. This is just one image showing it. So the comet really is shedding a lot of material, not only gas, but big 4 metre chunks of the surface are blasted off by the gas underneath. As the gas is evaporating, these holes, forming the vent holes, they blast out metres and metres of solid material, which goes out into space. This is still gravitationally bound, you can see that, but some of them do go out and they never come back. So we took tens and tens of thousands of images. There's all sorts of things I could show you. I was trying to figure out what to show you today, but there's a crack that has a pain in the neck. Poor old comet. There's a head and a tail, and we found a crack. And we were also listening to this with Philae on the surface. Now the crack, we're hoping as it went past the sun, the perihelion, it might be moving a bit, which is actually what causes this crack. We couldn't hear anything because poor Philae didn't wake up when we got close to the sun. But so Philae had 2 segments, the cold science and the hot science. So, but we saw this crack, and so this is more evidence that it's 2 bodies. And we, now this is the landing event. National Geographic came along and filmed a documentary there. I was in the control room when the landing occurred, and I just want to show you this video, which shows, I think, really well how exciting it was after 10 years of flying to get to the comet. Honestly, I have to be really honest with you. I didn't think we were going to make it because the complexity of the mission and the engineering was so complex. There were so many hundreds and hundreds of problems in that clean room. Every day of my life was a misery, effectively, trying to solve these problems. I really didn't believe we were going to get there. But as the mission progressed, we were able to modify the software and improve things. And then when we did, I honestly couldn't believe this day was going to happen. But this is what happened when we got the landing.
This is it. You are watching history being made. The first ever landing on a comet. I'm Dan Riskin. I am in the most exciting place on the planet right now, the European Space Agency in Darmstadt, Germany. And this crowd is cheering because an incredible group of scientists just put a lander on the surface of a moving comet. Now, they made it look easy, but this mission and what it's about to do are groundbreaking.
Okay, now I'm going to stop it there. It goes on for 1.5 hours, right? So, but it really is an amazing documentary, and it shows the whole thing. So we took a series of photos as we're going down onto. This is from Rosetta, looking down at the landing point, and the green square is where we wanted to land, and you can see that this is a before and after image, and you can see the dust cloud of the shadow of where we did actually touch down very close, within 150 metres of where we wanted. And confirmation that, yes, we'd hit the surface, the navigation was good, the deployment was good, but Philae wasn't there. We thought, oh my God, something's gone horribly wrong. So we could see the dust cloud, but we couldn't see Philae. So straight away we knew, we've got a few problems here. So then we went looking for it, and they processed some more images, and I think this is probably the most amazing image that ever came out of the Rosetta mission, or even any interplanetary mission, to be honest. This is Rosetta from 27 kilometres high in orbit over the comet, looking down as little Philae was coming down with its little triangular feet deployed. And it's drifting in this direction across the surface as we're looking down, as it's approaching its landing site, which is there, the touchdown point. And each of these images, we've zoomed in to actually get the detail to show that, yes, it is the triangular feet of Philae coming down. And 1543, we can see the footpads, the three little footpads of where, again, indeed, there's confirmation that little Philae hit the surface. And the before and after, so no footpads and footpads afterwards, so a difference of a few tens of seconds. And, but Philae wasn't there. So where was it? So at 1543, they sort of think, well, look, we know it's hit the surface. Can we see anywhere else in the image where it could be? And indeed, right up the top right-hand side here, there's a little white dot, which they realise that's Philae, caught by the sun in the dark shadow, just before it went outside the field of view of the image of Rosetta looking down. So we were extremely lucky to get it just within a few pixels before it left the image. Where it was going, what the direction, we could calculate the velocity from the time that it had gone. And so we actually had some information to say, well, look, it's heading off in this direction at a certain velocity, but we didn't know how high it was. Okay, it turned out that it was 1.3 hours. And, sorry, was it? No. Get the numbers down. Something like 1.3 kilometres, and it was about 1.5 hours of flight time before it touched down again. And in fact, I've got a 3D printed model of the comet here. And this is, in fact, extremely accurate in terms of its size and the shape and everything. And on here, I can show you the landing sites of... this is that rotating 3D digital elevation model. We can now print that. You can download this file from the ESA website. And you can make your own comet. So the green spot is the one there where the touchdown point is. That's where we wanted to land. That was where we found that it was in good sunlight. We could have a solar-powered lander, which is going very well. And the two yellows are where it bounced twice, and the blue was where we finally ended up. Okay? The red is where we put Rosetta down 2 years later. So everything's on the head of the comet, just because now you're interested to know, we've got Egyptian names for the comet. All the female names are on the head, and all the male names of the craters and features are on the bottom. And the reason is because women are more intelligent than men, and that's why the head was named with all the female Egyptian names. Okay, so I'm almost finished. So there's an image on the surface when we Philae touchdown, and we tried to find it. We took thousands of images trying to find where Philae actually touched down. And in this image, we found it. Can you see it? No? Okay, so there's the red square. Philae is inside that red square. We zoom in, and there it is, under a shadow, hidden in a crag on the head. Now these are some of the numbers. I won't go through those for too long, but it shows the 218 gigabytes of data got transferred from half a billion kilometres away. Tens of thousands of images. You'll see here that Roestta was the most busy station in all the telemetry and telecommanding. That's in Australia. It's another one of these Parkes Radio Telescope stories. You know, it was a huge Australian involvement, but most people don't even know the story until 13 years later when they made the Dish movie, for example. So Australia had a huge component in talking to Rosetta during its entire mission. And that is the end of my presentation. So, any questions?
One question for Warwick, I think.
Any questions?
Dave?
Thank you very much for that. I did a story for ABC Radio some months ago, and there was the comment made by ESA, I'm sure we quoted them, that these two bodies may have fused together. Is that under speculative, or is that still ESA's opinion?
Oh, yes, indeed. No, they are definitely two different bodies, because we've identified, again from this mass spectrometry in orbit, from Rosetta, orbiting around, that there is a slightly different chemical makeup to the head as there is to the body. Okay? Also, physically, they've got physical striations and layers in one direction on the head, and on the body they go in a different direction. So there's physical conformation, there's chemical conformation, and just the shape of the thing. We've got a crack in the neck, which shows that it's loosely bound. They are stuck together, but how strong we don't really know. But there's some ample evidence to prove that this is in fact two different comets stuck together.
What's your particular opinion on that?
Oh, absolutely. I'm absolutely convinced it's true. Yeah.
Okay, thanks. We might have to move on actually. A little bit behind time, so but we'll have time after this, of course, to quiz our guests at length. So thank you very much for that absolutely fabulous talk, and please accept the
Thank you very much.
token of our
Right.
thanks.
Thanks very much.